Can you now see the screen?
Yes.
So I'm Alan. I'm now going to present the calculating the Feigenbaum constant in a nonlinear RDLD circuit. So what I do is, because I'm one of the members in IPT, International Physics Prominent, I choose a problem that is about how to calculate some universal constant without using computer. And I think it's a very good paper to approach it. And last week I chose a paper that is released in 2014, and I just found one that is being updated about the methodology and about the research data. So I found this paper, but actually when I read it, this is not that as high quality as before, but they just release more data. So let's go through it. So I will talk about a few sections about chaos theory, experiment, about my thought about the paper, and some reflections. So about the chaos theory, as we know that when a butterfly, there's a saying, a butterfly flip the wings, and there will be cause some tornado from Brazil to the USA, and we can see from the animation below, there's a double rod pendulum. So at first it just swings like a simple pendulum, but when you getting more and more initial condition, more parameters, all the things become chaotic. So all this kind of thing is in a state of disorder and irregularity. So this kind of complex behavior can is only emerged in nonlinear dynamic system. It occur as like in the upper parts in nature, and also in the lower parts technology, that we can govern it and can utilize this to make some phenomena we want. And so how this kind of phenomenon being discovered is by Jay Feigenbaum. So he studied at electrical engineering at MIT and then changed to physics too. And after 10 years later, he worked in Los Alamos National Laboratory to study turbulence and fluids. And there's an opportunity for him to study chaotic map, just like logistic map. And then 1 year later, he discovered Feigenbaum constants. And then 3 years later, he published his paper about this kind of constant. And 4 years later, he have the guidance assistant by Oscar Lanford about how to prove it to be universal, not only focused on one type of nonlinear system. And 4 years later, he got the Wolf Prize in physics. So how he dealt about it is with the recursive equation, showing that xn plus 1 is equal to lambda xn times 1 minus xn. So what is xn? Xn is a normalized population at generation n. So lambda is a parameter that can cause this chaotic behavior in a nonlinear system. So this kind of parameter can cause repeated period doubling by increasing this kind of constant progressively, and then we can find infinite chaotic wave that are propagating and accumulated. So we see some kind of disorder and noise in the plot. And what Feigenbaum have discovered, there are two constants. The first one is delta, that is about the limit n tends to infinity with the ratio, that is the former difference of the parameter over the later difference of the parameters, and define it to be 4.669, and the lambda n is the parameter value at nth bifurcation occurs. So that is shown in the diagram, the plot at the right. So we see some bifurcation. And the second constant is about the ratio between the width of the time and the width of one of these time of these two subtimes. So we can find this has some ratio above the length between them. So how to demonstrate this kind of phenomenon is by the RLD circuit. So we see that the resistor, inductor, and also the diode is connected together in series. So when there is a periodic input driven voltage by the functional generator, we can see that with the 60 kilohertz, this is sinusoidal alternative signal, and then we have the nonlinear response from the diode. Then we can have some chaotic behavior, and at this time the parameter is the voltage. So we change the driving voltage a bit and a bit at each interval of the bifurcation. We can find the constant. So as long as we can find the nth bifurcation, so n tends to infinity, we can get our experiment close to the exact value, that is 4.669. And then we need to study the structure of the diode. So we know that a diode is a crystal containing two types of extrinsic semiconductor material. So there are some gap and fill the valence band and the conduction band. So with enough energy, the electron can promote the two conduction band and move freely with the applied E field. So we can see that this curve, we have a forward bias and reverse bias. So when we go to the forward bias, how can we do it? Is connecting the p-n junction to a generator with a positive terminal to p-type. So it allows the flow of the current. So when the electron flow through n-type, so it decreases the potential difference because it's negative charge, right? And then the electron move freely through the p-type, jumping between the holes. So as positive in p region and negative in n region, we have the electric field build up from p to n. So on the contrary, so reverse biased, we connect the positive terminal of the generator to n-type in reverse bias, as current is not allowed through the junction. So the electron flow through the p-type against the electric field, which hinder the movement. So that's why it becomes negative. The current becomes negative. Sorry. So this region becomes zero. Sorry, this region becomes zero. And then, so why does a diode cause chaos? So that's interesting question. So because we have the AC signal, that's the diode alternating between the forward bias and the reverse bias. So in reverse bias, in forward bias, what we expect is that the depletion region decrease in size because the combination of the electron and hole, so decrease the depletion region, and more electron can migrate through the diode. On the contrary, the reverse bias is that the depletion region increase, fewer electron can pass through. So what we expect is the longer time for the system to return to its reverse bias equilibrium. So reverse current unable to reach the equilibrium before the forward bias, and the increase in the E field due to the increase of the E field. So the next cycle will depend upon the P field cycle. That's why we have this chaotic behavior depending on the initial condition. And so now we talk about the data acquisition from the oscilloscope. So at the right hand side we see some plot that extracted from the oscilloscope. So what the researchers find is that the most resolution and clarity is at 15 kHz. And when we keep increasing the frequency, keep increasing the voltage a bit, we see the period doubling. And this fabrication occur at the initial peak speed into 2, as shown in the diagram B. And we keep increasing the frequency, increasing the voltage, so we find period 4, 8, so on and so on. And we get to chaos when we increase the certain value of the voltage.
Sorry, Alan, could you wrap up in a minute or two, please?
Oh, we have enough time. So the result is quite perfect because it lines with the 4.6 plus or minus 0.2 is quite close to 4.669. And it generates some logistic map that is how he get it to be 2.7 plus or minus 0.2, so only have the percentage error of 7. So I have some thought about this experiment is that they describe the topic briefly, and the con is that they haven't go too much about the methodology, because the system is quite subtle about the initial condition. It's just talk about impedance, capacitance, about this equipment, and there's a variation about the brand of the diode, and it has mentioned the capacitance of the diode, and the researchers should mention the resonant frequency because it matters. And I found that from the calculations that the chosen frequency from the researcher is not comparable to the resonant frequency. So I don't know how he got it to be the result he really wants. And I also have make my own setup about doing this kind of experiments. So I make a solenoid as an inductor, and I find some curves. But actually, this kind of curve is quite hard to be observable, and it's quite hard to determine a certain value that corresponds to that voltage to give the bifurcation, because I can enlarge the graph and I can also make it smaller. So it also govern how I count the number of lines. So I think the researchers should use the voltage against time to see how many oscillations, so to count how many bifurcation. And the reflection is that there is no derivation about this constant, so this should be fundamental, universal to all kinds of physics phenomena. And this kind of intuition is very simple because it makes us to view the nature in a different perspective. It's also inspired me to think of the previous presentation about Nobel Prize to embrace uncertainty is the road to predictivity. And I have my inspiration to do further research from the alpha to phi. Phi is a Fibonacci number. So what I can find is that if I find the ratio of the succession period doubling bifurcation, I can find some predictability of the Fibonacci number. Fibonacci number is the most chaotic and the most irrational number in the universe. If I can really find it, it will be some kind of original. And that's all for my presentation.
Thank you very much.
So is there any question?
Yeah, any questions?
Sure. I'm just curious about this comment you have on the recursive equation in slide 6, behavior.
This one?
Yeah. To me, the recursive equation is already written everything now. But then why you are stating that it's not only this equation, it's else you have in mind?
Sorry, I can't hear you. What is the question?
I'm just curious about the comment you left on the slide. I'm asking because to me, the recursive equation just is everything about the case. That's the case.
Why did you write not only this equation?
Because you can also set up the equation like sine, cosine, and also as long as it is only one-dimensional nonlinear system, you can also cause this kind of chaotic behavior in a plot. That's what I have found from some research paper, not only in this kind of representation of the equation.
Yeah, this is the most beautiful way of writing.
Yeah, it's really, really sounds still very. I thought the application to signal theory was interesting because it's kind of important for us experimentalists also. So maybe we should be more aware of the chaos in our signals. That was what I would take away from this. Any other comment or question? If not, thank you very much, Alan.
Thank you so much.